a really good evening or afternoon or morning, wherever you are calling in from. Welcome to our workshop today. Thanks for joining us for an introduction to geospatial cloud computing. I'm Sabrina Zito.
And I'm Julia Wagemann.
And together we are the co-founders of Thrive Geo. So Julia will be leading the workshop today as the lead trainer, and I will be your contact point for everything related to the community during and after our workshop. So a little bit about the workshop motivation for today. I'm sure many of you have heard of the terms geospatial cloud computing or cloud native geospatial, and you might have come across some of these acronyms or services that have been out there. And there's just almost an alphabet soup of acronyms, right? You have MPC, COG, you have Dask, you have Zarr, you have Xarray, you have STAC, AWS, GCP, and we want to help you make sense of this landscape of different services, cloud platforms, as well as libraries and data formats that have to do with geospatial cloud computing and cloud native geospatial. So what's today's workshop about? So we have a few key questions to answer. Why do we need geospatial clouds? What's the background for why we need these technologies? What does cloud native geospatial mean? And how do all these acronyms and fit all together? At the end of this workshop, you'll be able to define the term cloud native geospatial, describe key concepts and terms related to the cloud native geospatial technology stack, and also summarize what the geospatial cloud offerings are that are available to you. So right now we're in the introduction and icebreaker part of our agenda. We will have a two-part presentation following this. First part focuses on introducing you to geospatial clouds and the cloud offerings. Then we'll have some time for questions and answers after that. And then the second part will be on cloud native technology, the introduction to the stack, and also skills that you will need to use cloud native technology and data. Then we'll again have some time for Q&A. And then we'll close with a few next steps for what you can do. And then we'll have a quick self-assessment to see what you've learned today. And then we'll conclude our workshop together. So first up, a little bit about Thrive Geo. We are a newly founded company that's here to empower individuals and organizations to thrive with geospatial and Earth observation data. So we have so much data out there, and the amount is growing. The potential for using this to solve important questions and problems that we are facing today is really something that we would like to empower people to do. And we'll do this by providing training and upskilling. And we also engage in technical consulting as well as community building. And I'll hand this time over to Julia.
Thank you, Sabrina, and also welcome from my side. I'd like to also thank you for participating on the Slido and giving your confidence level. I'd like to remind probably those who feel already very confident, then there might be already not so many new things, but hopefully it will still be also of interest to you. So the first part is on intro to geospatial clouds and cloud offerings. So we'd like to give you a high-level overview on what cloud services exist, why we need geospatial cloud computing, and how you can also categorize different offerings that are available on the market. Good. A bit of background. So why we need geospatial cloud computing and how it started. Probably, I don't know how long you all have been part of the Earth observation and geospatial community and domain, but it has developed for like quite fast because we have to remember that before 2008, we didn't even have open data. So we still also needed to or the Landsat data, and then the data we ordered and needed to pay for individual scenes. And then since 2008, the open data policy was introduced specifically for the Landsat archive, and then it became quite broadly adopted also with the beginning of the Copernicus program in 2014. And with more and more open data, and of course, then also better technological developments, and also more and more better sensors, we have higher resolution data. We also need to find solutions on how to access the data and also how to process these large volumes of data. And so we see an exponential increase of open, but also commercial Earth observation data in the past decade. So since 2012, 2014. And there are just some statistics, for example, from NASA. It is projected that their archive of Earth observation data will increase or grow by a factor of 5 between 2021 and 2025. There are varying numbers about Copernicus, but just one number is that they expect, or they say that like just 16 terabytes of data per day is disseminated and also sensed or taken or observed. And then another statistics is that like we have already now a growing problem, but then also in the next until 2013, we expect that around 1,700 satellites are launched every year. So there is even more and more data coming, and on one side, it is like a really exciting time because we've never had so much great data available, which also gives us more and more opportunities to analyze and get insights. But at the same time, we have at the moment a very wild landscape of how data can be accessed, in fact. So with this growing volume of data, there is we have to reconsider our paradigm on how data is analyzed. So at the moment, we've been or in the past, usually there was like a data archive, and then you download the data, and then you did all your geospatial workflow and processing on your local computer. This is also still the option. So this doesn't mean that like, because we have like a lot of geospatial cloud services available, that there is no data downloadable anymore. So as I said, there is a vast or diverse landscape. And so there's still a lot of data that you have to download and then analyze on your local machine. But we have to start also like as users, starting breaking down a paradigm we've been trained to do. So looking for data, downloading them, and then analyze them on the local machine, to moving rather our code and our processes and analysis to the cloud. And we in the best case, we do everything in the cloud. So we discover data, the data is stored in the cloud. We can effectively access the data that is stored in the cloud. And then we also do the analysis and visualization. As I said already, there is a diverse landscape of geospatial cloud services available. So I expect that you've heard about most of them, specifically also from Amazon Web Services, then Google Cloud Platform. We have on Europe. In Europe, we have Wikio, which is like a community cloud for specifically for Copernicus data, or the European Open Science Cloud, which is specifically for researchers in Europe. And then we also have Microsoft Planetary Computer or Google Earth Engine. And this is just a selection. So from probably the most well-known, or just a really short, small selection. There's also other services available. But in principle, these cloud services can be organized or categorized in 3 different categories. So the one with Amazon and Google Cloud Platform, they're general purpose clouds, so they are not specifically or exclusively for geospatial or satellite data, but it is like cloud services where many different applications can run, but specifically also Amazon and Google, they offer open data registries and open data programs where they host satellite and geospatial data. Then Wikio and European Open Science Cloud. So you see this a lot coming from Europe as part of European Commission initiatives. There are so-called community clouds. So it's dedicated, so it's a cloud service that offers a selection of data for a specific community. So for example, Wikio, it offers access to Copernicus data. Or the European Open Science Cloud is specifically targeted and developed and set up for the needs for researchers and scientists and at universities. And then cloud platforms. So Google Earth Engine is the most well-known, and then just more recently also Microsoft launched and developed a platform that allows the very effective processing of Earth observation and satellite data. And there is dedicated tools and services available that are catered to the needs of users from satellite data. And so if we have a look from the options and also the flexibility between general purpose clouds and cloud platforms, there's always a trade-off that needs to be done. So general purpose clouds, they give you the highest and the best flexibility you can think of, but at the same time, to actually get started on general purpose clouds, you need much more information and expertise to set up your cloud environment in a way that also works in the best way for you. Community clouds is then a bit less flexible because you have already a selected offering from data and also services. And then cloud platforms, it is compared to general purpose clouds, the least flexible, but at the same time, the most adapted and offers the most tools and services you already need that you can get started. Good. So yeah, I think this is already what I just said. So like general purpose clouds offer a high degree of flexibility, but you need also advanced knowledge. And then on the other side, cloud platforms, they provide access to to also a subset of available data. It has a limited flexibility, but it is specifically tailored to needs of satellite data users. So some offerings where you can have a look and get started to access data offered on general purpose cloud. So Amazon Web Services offers a registry of open data. This is quite a large registry and archive, and so they have a fast collection which includes Copernicus data such as Sentinel-1 data from Sentinel-1, Sentinel-2, Sentinel-3, Sentinel-5P, but also data, for example, Landsat from USGS and NASA, and then also other selected data sets from ESA and other data providers. So yeah, have a look here. This is like definitely one of the fastest collections of satellite data available on the cloud. Google Cloud also offers a marketplace or like a dataset marketplace, but it offers a smaller collection and has a stronger focus on weather and climate data from satellites and models. So you will see here data from NOAA and from EUMETSAT, like the from meteorological satellites and also from ECMWF, the European Weather Center. So you find more here. For example, the open data from ECMWF you can find on the Google Cloud Dataset Marketplace. Wikio, as I said, is like a community cloud. This is implemented by European data providers like EUMETSAT and ECMWF and also the European Environment Agency. And it gives access to all the Copernicus and Sentinel data as part of the Copernicus program. And so you can have a look here. So on the screenshot, you see it's like you already, if you're not very familiar with Copernicus, then you have to, in the best case, already understand some of the terminology. But for example, you can look for data that is available under the climate service from Copernicus or under the atmosphere service. And then you can also look for the satellite instruments or the satellite or the instrument, and you can then find relevant data. And then two other community clouds. I will not go into detail here, but if you come across, we just want to give you a bit of help to better assess all the different offerings that are out there. So these are two community clouds, some of them also not directly open for anyone or for any users, but you have to be linked to, for example, you have to be part of the ECMWF member state that you can get access to the European Weather Cloud. Or for the European Open Science Cloud, it is specifically tailored for research organizations and academia. Yes, and then Google Earth Engine. This is definitely one of the, the Google Earth Engine really revolutionized and changed how a workflow on the cloud and can be done, and also how a lot of data sets can be already being made available in a very accessible format. It is the data archive is now already more than 90 petabytes of data that can be accessed from Google Earth Engine, and it is constantly growing. There are two ways how you can get started with Google Earth Engine. So they have in what you see on the screenshot here, the web browser or the web editor, which is in JavaScript. So there is a specific modified version of JavaScript that allows you to develop your scripts and your analysis workflows. But if you're a Python user, you can also use the Python. There is also a Python API to access Google Earth Engine and all the data. There is also now a strong integration with Google Cloud Platform. So if you have very intensive processing requirements, then there is now the link. So Google Earth Engine is one service offered on the Google Cloud, which allows you to really scale up your processes also as part of the Google Earth Engine service. And it is available. So it started as a strong community service, and specifically for researchers and for non-commercial use. And this also continues the way, but it is also now available for companies and organizations to use it in a commercial environment or commercial setting. And then another option on the cloud platform side is Microsoft Planetary Computer. This has been implemented by Microsoft, and it is linked with Microsoft Azure, so the cloud offering from Microsoft. This is also, they just started. They have now 24 petabytes of satellite and environmental data available. They follow a strong open source and community standard. So it uses all the relevant open source tools in order to be able to access data from the planetary computers. So you see already there is a Jupyter Hub interface in order to run scripts. You can choose your dedicated environment if you more a Python user or R, or if you want to integrate it with for machine, you want to use it for machine learning, then you can also have an environment with GPUs and TensorFlow. And yeah, so this is quite recent, but the data and the use will certainly also grow for this. Good. So let's now go to another terminology, what probably you all already heard in one way or the other, like for example on LinkedIn or on social media or in some other workshops and talks. We in the geospatial community, we talk a lot about cloud native geospatial, but we also often come across different meanings, or people use it in different ways. And one aim with this workshop is also to better, or to clarify a bit better on what cloud native geospatial mean, and also what the community has been it has been agreed so far, and where at least at the moment it looks like the direction also goes, and what community standards will be also seen in the next years around this term. So Open Geospatial Consortium is a standards body to define standards in the geospatial for location data in the geospatial domain. And the Open Geospatial Consortium also has a working group on cloud native geospatial and defines or has come up with a definition of this term. And as I say, it says it is a new way of working with spatial data that is centered around a set of new standards. And these standards are related to data formats, how to catalog and make data easily searchable and discoverable. So what metadata, how you can also how you store and make metadata available. And this set of new standards that is focused on dedicated to cloud-based access. So anything to make access and discovery, access and processing of geospatial data in the cloud more efficient. Good. And this is something what we want to clarify, because sometimes there's a bit of a misconception. So probably cloud native, we can say it is about how a process is done. So cloud native could be also that you don't necessarily have to process it in the cloud, as long as you follow all the specific standards. So if you use data in a specific in the cloud native formats, and you use STAC, for example, to discover data, then your process can also be cloud native. So it's about how you do things. And then cloud computing is about where the compute and the analysis is done. It doesn't mean that, like, so cloud native doesn't mean that everything needs to be in the cloud. It is more about how everything is done, from data discovery, access to processing. Good. So there have been a set of formats been developed in the past years that are particularly designed and structured for an efficient retrieval from cloud object storage, so from cloud services. And these cloud native data formats, they have some advantages. For example, that they are very efficient to access the data. So only the data that you actually need and processed is actually streamed. So this enables users a quicker development of your workflows, and it saves in the end time and also money. So using cloud native data formats gives you a greater efficiency. It also allows you to scale, because with these formats, they are designed for being very scalable and also parallelizable. So you can easily scale your data workflows, and if you have the data in the right format. At the same time, on the data provider side, it's easier to maintain, because they can disseminate their data without the need to run and maintain their own servers or databases. So there is not only benefits for users, but also for the data providers. And it facilitates overall tool development, because if a more efficient data access enables then in turn again the creation of other tools that help to interact with large volumes of data that is stored in the cloud. There is quite a few benefits which you will specifically notice once you access data in a cloud native format, and you all of a sudden really have the opportunity to access a lot of large volumes of data, which before, when you needed to download them, you actually didn't come to this level, because it was already too much to download, or too large of a volume to download. Okay, now let's go to part 2. So this is now all about, okay, how does this actually look technology-wise, and also what skills will you need to actually get started with cloud native geospatial? So to understand, okay, what are the different parameters and concepts or tools that are part of the cloud native geospatial technology stack. Good. So when we come back to our workshop motivation, at the beginning, we had like a lot of abbreviations and services and tools that are out there. So if we now think from part 1, we already covered all, like not all, but like the ones we had at the beginning of the workshop, like the data and cloud offerings. But then we have still quite a few left where we now want to help you to better bring them into along the geospatial data workflow or data analysis workflow. Good. And in the best way, so the cloud optimization happens along the entire geospatial workflow. So from data discovery to data access to data analytics and processing. So data discovery, you might have already heard. So STAC is the Spatiotemporal Asset Catalog. This is a standard that has been agreed within the community in record time, and this is now an agreed standard on how to make data hosted on the cloud discoverable and available. And then under data access, as I said already, we had a question already, okay, what are actually the data formats that help you to efficiently access the data? And they're specifically for raster data, 2 data formats, cloud optimized GeoTIFF, abbreviated as COG, and then also Zarr. And under data analytics and processing, you might have heard already about a Pancheo, which is also like a community around a specific set of tools that promotes a specific way how to, and best practices, how to analyze large volumes of multidimensional data. And so as part of Pancheo, they also recommend to use specifically for large volumes of multidimensional geospatial data, a combination of Xarray and Dask. So Xarray is a Python library that is very efficient to handle multidimensional arrays. And in the combination with Dask, it really allows you to parallelize and speed up your processing. And also lazy loading, which is very important, but I'll come to this So I will now go through each of these a bit more in detail. The Spatiotemporal Asset Catalog is abbreviated STAC, is a specification that provides a common structure for describing and cataloging spatiotemporal assets. It is based on JSON, and the feature is that it is indexable, and it uses standardized metadata fields. And as I said already, it has been agreed on with the community in record time, and there are already, so there's a specific standard specification, but then there's already 60 more than 60 application specific extensions. And so the aim with STAC is to increase the interoperability of searching for satellite images, so to make satellite imagery easier discoverable, because at the moment it's also not easy to actually know what data exists and is available. How STAC is organized, or they call it also entities. So there is a catalog, which is a container that links to other catalogs and collections. And the top level of the catalog is the root. And then a catalog can have different or multiple collections, and it contains, and the collection is, it groups similar items. So for example, from one data set, so from data from the same instrument or from the same region. And then under collection, you can have again other subcatalogs. It gives you really also quite a flexible way to describe your data offering. And then in each collection, there is an item. So, and this is usually a single scene or a set of data files that share the same geolocation, date, and time. And then each item is linked to an asset, and this is then the actual, or this is like a single data file that that is then linked. So this is how STAC is organized, from catalog to collection to item to asset. And this is how this could look like, a STAC catalog example. So you have here a description, and then you have your metadata and your items, and then in the end you have a link which you can integrate into your processing, and you can easily discover and access these items that are hosted or part of this catalog, of the STAC catalog. Good. So why do we need cloud optimized geospatial data formats? So why can't we actually just use NetCDF or GeoTIFF on the cloud? So these traditional formats, they're very efficient for on-disk access. So they're very optimized for accessing data on the disk or for download via smaller internal chunks. But in order to access data also in memory, we have to the data needs to be subsettable, because the more data we want to access, the more data that is loaded in memory. We have to be much more flexible in order to how we subset the data. And these cloud optimized formats, they allow the direct access of these subsets without an additional server that is needed, that subsets the data in the end. And this is basically, this gives a set of benefits. So first of all, we can scale because it is not on disk anymore, but it is stored on cloud object storage. It is more flexible because we can tailor the data access to specific needs. So you might also have come already across a compromise between making data optimized for spatial analysis or for regional analysis versus optimizing data for time series analysis. And this gives also a greater flexibility to tailor your data to your specific need. And it is also more cost effective because it reduces data transfers and also storage need. And for this reason, or this was the motivation to develop a set of cloud optimized geospatial data formats. And this is at the moment, so we also linked here. So one of the organizations that is promoting a lot of developments here is the Cloud Native Geospatial Foundation that is run by Radiant Earth, which is a nonprofit from the US. And we linked here a link, and there's another entry on a website. So there's different data types and there's different data formats being developed at the moment. As I already said, for raster and multi-dimensional raster, there is cloud optimized GeoTIFF and Zarr, but also for point clouds, there's a format being developed or under development at the moment, cloud optimized point cloud. And for vector, one of the formats is GeoParquet. There's also the table lists like on, okay, what is the status of the adoption and also the standardization of this format. And you see that like the two, like cloud optimized GeoTIFF is the widest, or the one that is most adopted or most widely adopted. And there's already also an OGC standard that is now open for comment. Then Zarr is less widely adopted, but you see some examples, and the standard is being developed. And then the standards for point clouds and vector is still more of a community engagement and development. So you see it less comment, and there is discussions on developing a standard, for example, for GeoParquet, but not for point clouds yet. Once we want to create or develop cloud optimized geospatial data formats, then there's so spatial is special because there is the challenges we face is there are different data types, and the optimization is strongly use case dependent. So if you, for example, are interested more in parallel reads versus partial reads. Good. So cloud optimized GeoTIFF is a regular GeoTIFF file and aimed at being hosted on a cloud storage with an internal organization that enables more efficient workflows on the cloud. So this is the definition also from the official website. How cloud optimized GeoTIFFs are organized. So there is a tiling which creates a number of internal tiles inside the image. So it makes smaller subsets of the image, and then it provides an overview. So and an overview is a creation of downsampled versions that match different zoom levels. And with this, it allows an easier and more efficient and faster access depending on what you want, what you need to stream at a moment during your processing and analysis workflow. And then there's a HTTP GET range requests, and this allows that a web client can only request the bytes that are needed from the server. And this is very important because this also speeds up the development, because only the data that is needed is actually streamed. So how this looks like, so basically on top there is the metadata that describes the data set, and then a cloud optimized GeoTIFF is organized in so-called internal file directories, which inform the HTTP client where to find any overview and also the actual data in the file. And important is that this clients that access a Cloud Geotiff uses only the information only to read the data that is needed for processing or visualization, but it doesn't read all the data that is described in this format. And so this is very important, and that's why it makes it very efficient and lean to work and process cloud optimized geotiffs on the cloud. Zarr is specifically coming from the climate community when you deal with multidimensional raster data sets, and this is a file storage format that allows you to efficiently handle chunked, compressed, n-dimensional arrays, and it is used to represent multi-dimensional raster. It, as I said, arose mainly from the needs from the meteorological and climate community. But a caveat is that if data from etcdf is converted to Zarr, it is a very heavy and bulky large file format. So it can be quite heavy because the metadata is stored externally from the actual data file. The data itself, the way it is organized, it creates many different subfiles that serve different chunk options for users. So this allows it to be very efficient, but at the same time, it is a very large file format compared to cloud optimized Geotiff. So here you see this is like at the moment the specification for Zarr is currently being developed. So the Zarr specification, it's the version 3, and there is a Geozarr standard working group that was formed working across leading data providers and organizations, so that really the community and also data providers. So it's not developed in silo, but really that there is like a community effort and agreement behind to make Zarr working for many organizations and users and applications. And this working group aims to define the conventions, how the geospatial data should be organized in order to be conformant to create a larger Geozarr archive. So if you're interested in there, we also linked here the website. You can follow also the developments here. So this has been quite recent, this working group. So there is a lot of development still ongoing. Yes, and then now we covered data discovery and data access. And now when we now go to data analytics and processing, we come back to Pangeo and the main two libraries that are recommended best practices are Xarray and Dask. So in case you also had at some point difficulties to understand how Pangeo, Xarray, and Dask all fit together. So Pangeo in principle is a community. So it is like a community of you and me, like users in the Earth observation and satellite domain, who came together and wanted to promote a set of best practices and tools that are recommended to use for processing of large volumes of satellite data. And so Pangeo is promoting a set of core packages. So it is not per se, it is not a software package by itself, but rather promotes the use of Xarray, Dask, and in combination also with the Jupyter environment. So Xarray, it is also has been developed from the climate or comes from the climate and meteorological community, and with the motivation to have a very efficient and flexible Python package that allows the handling, efficient handling of multidimensional arrays. And this is also now around already for, I think less than 10 years, but X-array is very widely adopted, and it is the basic data structure for also all other Pangeo core packages. So once your data is in an X-array data format, it gives you a high flexibility to then process and use other packages and tools in order to process the data in the way you need. And then in combination or together with Dask, so Dask is a Python library for parallel computing, and into the X-array format, there's already Dask integrated if you have the Python installed. And the really nice thing is that, like, for example, if you have large volumes of data and you have them in an X-array format, you can develop your workflow, you can bring data into one X-array of several gigabytes of data, and you still can develop the workflow because Dask allows you to do the lazy loading. And with lazy loading, it means that there is a capability to represent the large data set without actually loading it. And so you develop your workflow and you see also already how the X-array structure of the result would look like without actually processing it. And it is just processed once you then say, okay, now please process it, or please visualize it. So when you actually want to access the actual data. So this really is very helpful to develop workflows on top of large volumes of data. Good. And so how this works in combination of all the other packages of Pangeo. So basically you have data storage, then you have Dask, which helps you to parallelize your computing. So there's different nodes where you can then also process or where your workflow is also split up on different processes and schedulers. Everything is in an X-array format. And then you as a user, you access the data or your data workflow, ideally via a Jupyter environment in the browser. And so this is the recommended best practice. And this is also where the community agreement goes to, and where a lot of like big data processing workflows are done nowadays. I will now come to the last slide on what skills and knowledge is needed to get started. So first of all, there's don't be afraid to get started, because this is like an exciting field, and I'd like to invite everyone to approach this new journey or to get started with curiosity. So it helps, of course, when you start on to to have this high level overview, because then you also can ask the right questions, or you can better assess if you have the correct terminology, then you can also better describe what you actually want to do. And then there's like, as you also start probably with coding or with programming, so also get familiar with the community and also with the leading organizations who are pushing things and developments forward related to cloud native, because then you also know where to look to find specific answers. So to how to work with the cloud native formats, for example, or how to work with the Pangeo environment or the Pangeo best practice and recommendations. So definitely with cloud-based or with cloud-native workflows to spice up your coding. So anything like also when you're working on the cloud, be familiar with working in a terminal, also knowing how to navigate through file systems, and specifically then also learn how to navigate or work with cloud native formats. And with this, the standard that has developed specifically for satellite data and meteorological data is Python. And then specifically, if you use Google Earth Engine and a web editor, then there's also JavaScript. But like in order for the cloud native workflows using STAC and also the cloud native formats, Python is the go-to language. And then always very helpful is also to have knowledge about how in general the data of like satellite data and also meteorological data is structured, and how these formats are, so that you can also understand what the data formats describe. With this, I will hand over again to Sabrina.
All right, thank you, Julia. So we're going to wrap up with a few key points and resources for you so you can get to see what the next steps are in this geospatial cloud computing learning journey. So today we started with a sea of acronyms, and some of them may have been unfamiliar to you. And right now we've organized this array into something more manageable. So we covered important players or examples in the cloud landscape, examples from general purpose clouds, community clouds, and cloud platforms. And we also shared a bit about the geospatial workflow, what you can use for data discovery, what are some formats that you might encounter when you're trying to access the data, and what are some Python libraries and best practices that you can use for doing data analytics and processing. So to sum things up, today we covered geospatial cloud offerings and how they differ in their target audiences and the level of customizability. We shared how cloud native geospatial is a set of recommended standards on how to conduct geospatial workflows on the cloud. And we showed that there are different sets of concepts that are still in development and are evolving for each of the different phases of this geospatial workflow, and with the aim to become widely adopted standards. So here are some resources that you can take a look at for your next steps on geospatial cloud computing. We will share these links with you, and you can take a look at, for example, the NASA Earth Data Cloud Cookbook, which includes also Jupyter notebooks and examples. Radiant Earth also has some guides and useful information on the Cloud Native Geospatial Foundation website. And you can take a look at data on the Registry of Open Data at AWS or the Google Cloud Data Marketplace. Listen to a podcast episode from Mapscaping on Cloud Native Geospatial, and also links to checking out Google Earth Engine and Microsoft Planetary Computer. And of course, you can also read more about the standards that are being developed on the OGC Cloud Native Geospatial page. So we'd like to say again a huge thank you for joining us today.
Thank you. Bye.
All right. Goodbye.